Yaskawa. You are watching the What's New with MotionWorks IEC 3 video series. Today's topic is going to be about the MP3000 IEC series networking modifications. Hi, I am Micah Studeman, and in this video I am going to explain the Modbus TCP and Ethernet IP modifications, along with some function block additions that were made for the MP3000 IEC series motion controller. Let's start with a quick overview of the Ethernet IP protocol. Ethernet IP is a protocol that uses instances to communicate between scanner, otherwise known as master, and adapter, otherwise known as slave, devices. The MPIC controllers can either be set up as an adapter device, being controlled upstream by a PLC, or as a scanner device, which would control remote I/O or other adapted devices. They can also be both the scanner and the adapter device at the same time. These setups are the same for Modbus TCP as well. In the MotionWorks IEC hardware configuration, we can see the instances that can be used when the MPIC controller is set up as an adapter. MotionWorks IEC 3 has increased the number of instances available to the MP3000 IEC controller, thus allowing more data to be transferred. Specifically, 10 input and 10 output instances have been added, and each of these instances are 2 to 4 times larger than the previous instances. Another change that was made for the MP3000 IEC motion controllers allows them to have more Ethernet IP adapters connected when they are set up as Ethernet IP scanners. MotionWorks IEC 3 allows up to 100 adapters to be connected to the MP3000 IEC controller, which is 5 times more than before. This is useful for times when the motion controller is being used as a data storage or transmission hub. Ethernet IP isn't the only protocol that has been modified in MotionWorks IEC 3. Modbus TCP also has some improvements that were made for the MP3000 IEC controller. MotionWorks IEC 3 has increased Modbus TCP function code sizes for the MP3000 IEC controller. This allows more data to be transferred between the MP3000 IEC series motion controllers and other Modbus TCP master devices. The increased function code sizes can be seen in the Global Variables worksheet after the motion controller is set to be a Modbus TCP slave in MotionWorks IEC 3 hardware configuration. An option has been added which allows the Modbus data to be stored in the %M memory area on the MP3000 IEC controller. Using the %M memory for the holding registers allows any of the network devices to read from the same variable, and it allows less memory to be used to hold the requested data. For example, let's say that we have a HMI being the Modbus TCP master and the MP3000 IEC controller being the Modbus TCP slave. The HMI puts data into the Modbus holding registers via %I memory. The motion code then uses the data in the %I register. If the HMI wants to see what the holding register value is, it would have to duplicate the %I holding register value in the motion code and put it into a %Q holding register, which can then be read by the HMI. Now when %M memory is used, the holding register is bidirectional, so the HMI can write to it and read from it. The motion code does not need to duplicate the value for the HMI to see what value it had written. The %M selection can be found in the hardware configuration of MotionWorks IEC 3 under Modbus TCP. Finally, MotionWorks IEC 3 introduces 2 new function blocks to deal with the data format otherwise known as endianness. Network data can be seen using either the big endian format or the little endian format. The MP3000 IEC series controller has a big endian processor, where the MP2000 IEC series controller has a little endian processor. The endian function blocks need to be used when using the %M memory and when sending structures or arrays between a big endian and little endian device. Most HMIs have a setting to convert the data that it is receiving. If this is set, nothing needs to be done on the controller and the data still shows correctly. To explain how the function blocks work, I will use this diagram. Let's say that we have a little endian controller as a network slave and a little endian HMI as the network master. The controller sends 1234 5678 as a 32-bit hex value to the HMI. Since it is being transmitted in the little endian format, the least significant word is transmitted first, with the most significant word being sent last. Since the HMI is little endian, it gets the value correctly and displays it as 1234 5678. Now let's replace the little endian controller with a big endian controller. Let's send the same 32-bit value. Now the big endian format sends the most significant word first. Thus, when the HMI gets the 32-bit value, it puts the most significant word in the least significant word's position, thus showing the value of 78563412 on the HMI. The new big to little endian function block converts the sent data from big endian to little endian. so when that function block is used, the value shows correctly on the HMI. The other new function block converts from little endian to big endian. So let's look at the diagram here. Let's say a little endian HMI sends 1, 2, 3, 4, 5, 6, 7, 8 to a big endian controller. Like before, with no conversion, the value will be shown incorrectly on the controller. But if the little to big endian function block is used, the motion controller gets the correct value. More information on endianness can be found on Yaskawa.com in the tn.mpic.02 app note. Thanks for watching this video. Go to yaskawa.com/IECSW to download the latest version of MotionWorks IEC 3 and try out these features yourself with the 30-day demo.